Algebra 2 students, hopefully by now you've got a pretty firm grasp on how the degree and the leading coefficient tell you what happens within behavior. What happens at the ends of the graph. Yesterday or Tuesday, you looked at what happens with a polynomial function when we can see the roots, when we can see the x-intercepts, and what happens if they're repeated and things like that. Now the question is, how do we go from this to that? So how do you take a polynomial that's not in factored form? 2x to the fourth plus x cubed minus 19x squared minus 9x plus 9. And how do we get it to this? And I'll tell you, I can't look at this polynomial and know this is true. But what I can do is I can figure out, because I know some more math than you, what I can check to see if works in factoring this polynomial. So you worked with quadratics in the last unit. How do you take a quadratic to factored form? How do you take a polynomial to factored form requires just one extra skill. That skill is called the rational root theorem. The rational root theorem, I'm not going to worry too much about what it says and making you memorize it or anything like that. I want you to get the idea. So it starts and says, if you have a polynomial where every single one of the coefficients are integers, so that's positive or negative whole numbers. So you got to start with integer coefficients. If you have integer coefficients, then if this polynomial has rational roots, that's zeros in the form of a over b, right? A rational number. If this has rational roots, they will be of the form the factors of the constant divided by the factors of the leading coefficient. So what the rational root theorem does is it takes a polynomial like this f of x, and it allows us to say, hey, I've got integer coefficients. So now I know that if this thing has any rational roots, they're going to look like the factors of the constant. So that's 1, 3, and 9, divided by the factors of the leading coefficients. That's 1 and 2. Now, we also have to account for positive or negative. So the factors of 9 could be 9 and 1, or they could be negative 9 and negative 1. The same with positive 2. It could be 1 and 2, or it could be negative 1 and negative 2. And now what we do is we list from this here, we can list all the possibilities. 1 divided by 1 is 1. 3 divided by 1 is 3. 9 divided by 1 is 9. 1 divided by 2 is 1 half. 3 divided by 2 is 3 halves. And 9 divided by 2 is 9 halves. Now again, you have to account for positive or negative. So this theorem tells us if the polynomial we're looking at has rational roots, then they will be of the form, they'll be one of these 12 numbers. There's 6 numbers here, but positive and negative of all of them. Now you got to go back to when the rational root theorem was first proven, which I believe was somewhere in the 17th or maybe even earlier century. They couldn't waste their time on Reddit. They couldn't waste their time with Rubik's Cubes. So to have some polynomial function where you had theoretically an infinite number of possible rational roots. To narrow it down to 12 possibilities was awesome, because now we can just check these 12 numbers and find them. And the trick is, we really only need to find 2. Because if we can find 2, we'll be able to rewrite this polynomial as 2 factors times a quadratic. Now, remember, factoring comes from multiplication. We call it factoring because we're rewriting multiplication. So when you have 72 and you factor it to 8 times 9, you're trying to rewriting multiplication. A useful skill when rewriting multiplication is division. So we've talked about adding and subtracting and multiplying polynomials, and now we are finally going to talk about how do you divide polynomials. Because we got to be able to divide these factors out to see what happens here. Okay, so I'm going to clear the screen. Let's look at this factored form. The factored form has these factors here. So I'm going to use this as a cheating method. So notice the zeros. This gives you a 0 of 1/2. This gives you a 0 of -1. This gives you a 0 of -3. And this gives you a root of +3. If you go back and look at your notes from what I just erased, you will see all 4 of these numbers were on our list of 12. 1 +1/2, -1, -3, and 3. So let's talk about how do you divide a polynomial by a factor. So you divide a polynomial by a factor the same way you used to divide when you were in lower school. So a little bit of a review. How did we use to divide 17 by 4? Well, instead of writing it as 17 over 4 like we do now, we started by saying this. What is 17 divided by 4? And then we learned this way of division. And we'd ask ourselves, what times 4 gives us 17? And we can't think of anything because there is no integer that times 4 gives you 17. So we would say 4 because that would give us the biggest number that is smaller than 17 that would get us close. That's less. That would have a difference of less than 4. So then we would take 4 times 4 and write that here, and then we would subtract that, right? So we would minus this, and we get a 1. And then let's go way back in lower school and stop right there and say, okay, we're done. This number is smaller than 4. So what do I have? I have 17 divided by 4 is equal to 4 remainder 1. All right, so how are we going to divide polynomials? Well, we're going to take this polynomial, and I'm going to cheat a little bit here because we usually don't know this. We're going to take 2x to the 4th plus x cubed minus 19x squared minus 9x plus 9. And we are going to divide that by x minus 3. So, how do we do this? Well, we start with 2x squared plus x cubed, 2x to the 4th. Here, let's just clear this off. So we start with 2x to the 4th plus x cubed minus 19x squared minus 9x plus 9. And we divide that by x plus 3. All right, so we're going to start with x. What times x gives us a 2x to the 4th? What could I multiply x by to give me a 2x to the 4th? If you said 2x cubed, you're correct. And now we take this 2x cubed and we multiply by x plus 3. And that would be 2x to the 4th plus 6x to the 3rd. Now, just like we did with 4 times 4 is 16, we now subtract this entire number. Now what I do is instead of subtracting this entire number, I change the signs and add. Because adding is much easier than subtraction. So 2x to the fourth plus the opposite of this is 0. If you don't get a 0 here, you mess this up. So go back and start over. You should always get a 0 first, because this should cancel out. Now we take this 2x cubed, we multiplied it by 3, we get a positive 2x cubed times 3, positive 6x cubed. Now I'm going to take x cubed and I'm going to add the opposite of this, or I'm going to subtract 2x cubed, or sorry, 6x cubed. And that gives me minus 5x cubed. And then remember, like with division, you can bring all this down. Minus 19x squared minus 9x plus 9. And now we do it again. What times x gives me a negative 5x cubed? Well, that would be minus 5x squared. And now we take this minus 5x squared and we multiply by x. And that gives us minus 5x cubed. Again, those first numbers need to match. Then we're going to take minus 5x squared, multiply by 3, and we're going to get minus 15x squared. And then we're going to subtract that whole difference. But remember, I just like to add the opposite. So now I add these up, and I get negative 4x squared. If you notice, I just skipped this because I know it's going to be a 0. Now I begin the process again. What times x gives me a minus 4x squared? Well, that would be a minus 4x. And now I multiply by, I take this minus 4 and I multiply here. I get minus 4x squared. And then I get minus 12x. Now I change the signs and add. When I add these up, I get a 0, and now I get 3x plus 9. Now I ask myself, what times x plus 3 gives me, or sorry, what times x gives me a 3x? And the answer is a positive 3. So then I multiply and I get 3x, and then I get plus 9, and now I change the signs and add, and when I add, I get 0. What that means is x plus 3 evenly divides this polynomial. Or said another way, x plus 3 is a factor. So now what do I have? Well, I can rewrite this polynomial as x plus 3 times 2x cubed minus 5x squared minus 4x plus 3. And I found one factor. There you go. Now we get to do the process all over again, but this time with that polynomial. Right? We're going to leave this factor out because we've already found one. So I got to clear the whole screen, unfortunately, but now I'm going to take 2x cubed. Here, let me clear it again, give myself some more room. 2x cubed minus 5x squared minus 4x plus 3. And I'm going to divide by another factor. And that's going to give me x plus 1. Right? Negative 1 was a 0. So I just do this again. I'm going to go quicker now. 2x squared, that gives me a 2x cubed plus 2x squared. Change the signs and add. When I do that, I get a minus 7x squared. What times x gives me that? Well, that would be a minus 7x. Distribute that here. Get minus 7x squared minus 7x. Change the signs and add. That gives me a positive 3x. What times x gives me a positive 3x? That would be a plus 3. Distribute, get a 3x plus 3. Change the signs and add, and you get 0. So now, from the previous problem, we knew that x plus 3 was a factor. I've now shown that x plus 1 is a factor, and I'm left with 2x squared minus 7x plus 3. 2x squared minus 7x plus 3. And if you can't factor 2x squared minus 7x plus 3, then I need to change your grade from the last unit because this is a quadratic. And we should know that 2x squared minus 7x plus 3 is going to factor to a 2x and an x, and then we'll have a 1 here and a 3 here, and 2 times this would be a 6, and 1 times this would be a 7. I need a negative 7 and a positive 3. There we go. And if you look, we've taken this polynomial and written it as a factor in factored form. And that allows us to draw the sketch that we were practicing earlier. So how do we draw the sketch? Well, we know it's an even degree. We know it's got a positive leading coefficient, so it starts up and it ends up. We know it crosses the x-axis at -1, at -3, and we know it crosses at 1/2, and we know it crosses at +3. So now, starts up, flies right through, turns, flies right through, then what's it do? Turns down for what? To hit that x-intercept, and then it has to turn up to hit that x-intercept. Notice no repeated roots, so all of these zeros happen exactly once. That's why the polynomial function just flies right through and has what we call a sign change, because the y values change signs, right? Below the x-axis, it's negative. Above the x-axis, it's positive. So there's always a sign change with an odd multiplicity, right? If it was a 3, it would just flatten out before it has the sign change. If it's an even multiplicity, it bounces and there's no sign change. So it either bounces back down or jumps back up. But now look, I can just mark this y-intercept as 9, right? Because the constant's always the y-intercept. And I've got a pretty decent sketch. Many of you had a note on your last test to label your axes. So I'm going to start taking points off for that. You have to label x and y. And now, because we were able to take this polynomial function and put it in factored form using polynomial, what is called long division, polynomial long division, we were able to check these factors. The rational root theorem gave us the candidates, right? Plus or minus 1/2, plus or minus 3/2, plus or minus 9/2, plus or minus 1, plus or minus 3, plus or minus 9, found by taking the factors of the constant over the factors of the leading coefficient, right? Again, notice there's a 0, there's a 0, there's a 0, there's a 0 again. The 4 zeros, the 4 roots showed up by the rational root theorem. How did I know to check those 4 and not the other 8? Well, I cheated and I knew the example. You're just going to have to brute force check them all. And if it's a 4th degree, you really hope you find 2 right away and hope you're a good guesser. We'll talk more about that in just a minute. But just recapping this whole problem, how do you use that rational root theorem to get this stuff together? Well, you just check using polynomial long division. All right? So I'm going to give you a practice problem for polynomial long division, and we'll go through that next. All right, with this example, one thing I want you to notice is that there's no function here. We're just doing one polynomial divided by another. And try this example on your own. I will give you a hint. The hint is there's a remainder. So this time the problem ends not with a 0, but with a remainder. And how do you know there's a remainder? Well, I'm going to give you a hint. Remember, with 17 divided by 4, the reason we knew there was a remainder of 1 is because we got to something smaller than 4. So when you're dividing by x, if you get to something smaller than a first degree polynomial, you're done. Okay, if you were dividing by x squared, you would stop if you had something that was smaller than a quadratic polynomial. All right, try this example. All right, if you didn't pause and try the example, you're missing out on all the fun. So x cubed minus 4x squared plus 2x minus 3. divide that by x plus 2. What times x to get an x cubed? X squared. Multiply that in. X squared plus 2x squared, x cubed plus 2x squared. Now what do? Change the signs and add. Get a minus 6x squared. Now what times x gives me a minus 6x squared? That would be minus 6x. Multiply that in and you get a minus 6x squared minus 12x. Change the signs and add. When you add that up, you get a 14x. What times x gives you a 14x? Well, that would be plus 14. Distribute that in, get a 14x plus 28. Change the signs and add. When you add that up, you get a minus 31, and that's your remainder. I know that's the remainder because the only thing I could multiply x by to get minus 31 would have an x in the denominator, be minus 31 over x, and that's when you stop. This is a linear polynomial. This is a constant. This is a smaller degree than this. That's the remainder. So, what's the answer to this question? What is x cubed minus 4x squared plus 2x minus 3? Well, what is 17 divided by 4? Well, it's 4 remainder 1, but we don't write remainder 1. We say it's 4 and 1/4. Right? And when we say the word and, we mean plus. It's 4 plus a fourth. That's the remainder. There's 1 left over from dividing by 4. So what's the answer here? Well, the answer to this is x squared minus 6x plus 14 plus a remainder of negative 31 divided by x plus 2. That's it. If you were to get a common denominator with all 4 of these terms of x plus 2, it would simplify to this. These two things are equal. And here's how you write that answer. Good? Now I'm going to do a fancy screenshot here. I hope it works. Okay, good, it works. I'm going to take a photo of this. Oh, it doesn't want to work with the marker. Darn it. So I think I got away with my video making program to take a screenshot of this because I'm now going to show you the shortcut for polynomial long division. You knew there was a shortcut, but I didn't want to tell you till now. There is a shortcut, so we'll make this work. All right. So 1 second. I'll be right back. All right. So here's the shortcut. I know you all want the shortcut, especially Nelson. The shortcut only works when you're dividing by a linear factor. So if you're going to take x cubed minus 4x squared plus 2x minus 3, and you're going to divide by a linear factor like x plus 2, the way the shortcut works is you write the coefficients of the polynomial. 1, negative 4, 2, negative 3. And then you, in this little box, this little half box, you put the value that would make what you're dividing by 0. In this case, you're going to put a negative 2 here. And then you drop this 1 down. You take this number, multiply by 1, and you get negative 2, and you add these up. Negative 6. Take this number, multiply by here, and get positive 12. Add these up. You get a 14. Take this number, multiply by 14, write it here, get a negative 28, and negative 31. The way the shortcut works is I have taken 1x cubed minus 4x squared plus 2x minus 3. And I've divided by x minus a negative 2. When I've done that, the answer is right here. 1x squared minus 6x plus 14, and the last number is the remainder. So plus negative 31 over x plus 2. So in that shortcut, don't write what's in the gold pen here, but just what's in the black. But look at where these numbers come from. Why do we put a negative 2 here as opposed to a positive 2? Well, the best way I can think of is, well, don't we change the signs here every time we're adding up? So we're going to change the sign first. And then why do we just drop this 1 down? Well, look, that leading coefficient just comes right here. And then look where these numbers are. Do you see the negative 6 right here? Negative 6. Do you see the 14 right here? Do you see the negative 28? Right? Do you see the 12? Do you see the negative 2x? All of these numbers are in this little shortcut. It just doesn't have all this mess here. Good? So I know this is a long video. I know I'm talking a lot. But here is the recap so far. Let me clear this off. Here is the recap of everything we've done today. So one, we have this idea called the rational root theorem. The rational root theorem tells you if you have integer coefficients, how you can get good guesses for zeros or roots of a polynomial. How do you get good guesses for zeros? And that's by factors of the constant over factors of the leading coefficient. Factors of constant over factors of leading coefficient. Once you have your good guesses, how do you check? Well, you got to be able to do polynomial division. And we're going to be using this skill to check for factors. But polynomial division is just a skill, and you can divide any polynomial by any other polynomial of a lesser degree, provided that you just practice that skill. And then in the special case of dividing by a linear factor, you can use a shortcut that I just showed you called synthetic division. When you do synthetic division, it's a shortcut of polynomial long division, and it only works for linear factors. Good? I know this is a long video, but I still got to show you there's just so much to do. Here's the last little caveat, and then I'm going to call it good, I promise. If you look at this linear factor, this gives you an x equals 0 of positive 1/2. If you had used synthetic division here, 2, 1, negative 19, negative 9, and 9, the value of x that makes this 0 is 1/2. So when you do division here with a 1/2, that's fine. Drop the 2, multiply by 1/2, get 1, multiply, get 2. Multiply by 1/2, get 1, add them up, get negative 18. Multiply by 1/2, get negative 9, add them up, get negative 18. Multiply by 1/2 and get negative 9, add them up and get 0. The remainder is the last number. The remainder is 0, meaning x minus 1/2 divides this polynomial evenly. And it divides it with another factor of 2x cubed plus 2x squared minus 18x minus 18. And do you see that every single one of these numbers has a factor of 2? And if you force that factor of 2 out, you would get this. And if you then took this factor of 2 and multiplied it into here, you would get 2x minus 1. So when you use a 0 that is a fraction, whatever is in the denominator, there will be a common factor of that if it divides it evenly. So just something to be aware of if you're checking a fraction. All right, super long video, but we're running short on time. So go back to this video. If you watched it on double speed, watch it again because there's a lot of important information. Tomorrow, after the quiz, you will be practicing with the following things. You will be practicing 1, the rational root theorem. 2, polynomial long division. 3, synthetic division. All right, peace.